we had just completed presentation of first order calculus and then started with the tabula for the first order logic. So, we called it FT. Let us give the rules again. It is all the rules of propositional tabula, and then we have some rules for the quantifiers, and then maybe equality, right. So, the rules were for all which it looks like for each x, then from this you conclude x by t, okay, and then repeat the formula. So, which signals that it can be reused. Earlier we are not writing it because you need not reuse, but now here you can always reuse them, and we have something for there exists rules, existential rules, where you cannot repeat, that is why you should specify. So, this not for all is an existential rule which looks like not for each x, from this conclude not x by t, where t is new. So, to start with we will take that t is a new constant, So, new means here new to the path where you are developing the tabula. We will see later how to modify it, so that it will be easier or it will be better to apply. That means the tabula will be shortened, but to work with that will be a bit difficult, because we will be going to relax the rules on this new. Now, this new constant means the constant t never occurs in that path of the tabula, then you can give it. Then we have there is rule which is similar to not for all. It says there is x, then you can conclude x by t, where again t is new, is a new constant. Then we have not there is rule which is universal. It looks not there is x, then you have not x by t for any term t, and you can reuse the formula, okay. And we had rules for equality, which is equality its reflexivity, which says anywhere in the tabula you can introduce t equal to t for any term t, right. So, we do not need anything to be present here, anywhere you can introduce it. Then you have substitutivity of equality, which says that if you have s equal to t and also another which is having x by s will be occurring there, they can introduce x by t, okay. It is similar to our equality axiom, right, A7. Okay, let us see some examples. I am not repeating the PT rules, they are for the connectives as earlier. Okay, let us see. So, you can start with the examples as our axioms of FC, see how the tabula proceeds there. So, first three things we have verified with PT, right, first three axioms, they are the propositional ones. Axiom 1 like x implies y implies x, so go on applying propositional rules. So, let us take with the universal rules. So, one our axiom was A4, it looked like for each x implies x by t, right, this was our axiom. So, here t should be a term for which x is free in x, okay. So, now you want to show that this is a tabula theorem. So, again we will use the same symbol turnstile to say that it is a tabula theorem. If there is confusion you can say PT earlier, right. Now, you can write FT. If there is another system and this also, then you have to give the subscript, otherwise we forget it. So, now you are doing with tabula. So, the tabula rule says that to prove something to be a theorem, you start with the negation of it, and then see that some tabula closes. For the consequences, you take all the premises, negation of the conclusion in the root, then so that there is a closed tabula for it, right, with the expansion rules. So, we start with not of for each x x implies x x by t, okay. Then not implies rule is applicable, not p implies q, which is p and not q, both p and not q will be in the same path. So, we say for each x x not x x by t, right, it is because of not implies rule. Then we use for all rule. So, that directly gives x x by t and the tabula closes. Okay. If you want to mention the rules, so here we are using not implies, here you are using for all. Okay, clear? Let us see another axiom. So, for equality we have the other axiom, for each x, x implies y implies x implies for each x y, where this variable x is not occurring in capital X, let us say, right, x does not occur in x. Okay. This is our next axiom. Yes. So, now how do we proceed? We want to show that this is a theorem in tabula FT. So, start with the negation of it. For each x, x implies y implies x implies for each x y. Okay. So, again not implies is applicable. So, it is for each x, x implies y, and not of x implies for each x y, again not implies. So, that gives x not for each x y. Okay. Now, here you have for each x, x implies y and not for each x y, fine. So, which one to use, this one or this one? Both of them you can use, no problem, right. If you use this one suppose, so what does it give? It gives x implies y some x by t, x may be occurring in y, x does not occur in x. So, even if you take x by t, it has no effect on x, it is same, right. Next you go for not for each x y, that gives not y of what? From this you cannot use t again, right, because t should be new to that, but t is already occurring in the path. So, you cannot use, that becomes a stumbling block. Of course, this is not a problem. If you can use s, after using s you come back to this, use again for that s, because that can be reused, it is universal. So, this sort of repetition can be avoided if you first do this, use on this, then use on this, right. So, this is a nice heuristic to be followed in tabula, just as in PT you are doing, if it is a branching rule or a stacking rule, use the stacking rule first, so that branching will be less. Now, it is a sort of branching here, though in the same path there will be repetitions. So, if there is a choice between existential rule and universal rule to be applied, apply the existential rule first, that will shorten the tabula, right. So, let us use on not for each x y, that gives not y x by t, t is new, you can say constant also c, that is all. Then we can use the for each gives x implies y x by t, and x implies there is no modus ponens, no? Yeah, there is no modus ponens in tabula, you have to use tabular rules. Okay. So, tabular rule says it will branch out now, one with not x, another with y x by t, implies rule. You do not need anything else, that is what tabula is for, it is complete by its own. So, then this is a path where not x and x is there, so this closes. This is a path where y and not y are there, so that also closes. So, let us see equality. So, you want to show that t equal to t. You have to show by tabular rules, right? It is direct, but you have to show a proof. So, for the tabula formally we have to start with negation of that. Yeah. So, you start with not of t equal to t and introduce t equal to t, this is your equality R rule, then close it, right. This is what tabula asks us to do. Fine. Then we have the other axiom for equality A7. What was that? S equal to t implies x x by s implies x x by t, right. So, take the negation of the whole thing, which is s equal to t implies x x by s implies x x by t. Okay. Then not implies is applicable. So, we have s equal to t and not of x x by s implies x x by t, again not implies. So, x x by s not x x by t, right. Now, we have s equal to t x x by s, therefore, we introduce x x by t, that is substitutivity of equality, okay, from this s equal to t x x by s. Now, it closes. So that this is a theorem, there is x, well we will take there is y, p y implies p x. Such sentences will never come from natural languages, but it can come in mathematics, existential quantifier with implies. It can be vacuous sometimes, but let us see how do we proceed. So, we will be starting with negation of there is x, there is y, p y implies p x. In fact, if you look at this, this says there is x goes through, right. This will be equivalent to there is y p y implies there is x p x, which is simply renaming. Okay. This there is x goes through this where x does not occur. So, it becomes there is x, there is y p y implies there is x p x, which is simply renaming. Y is renamed as variable x, that is all on the right side. Okay. So, it should be correct. Now, in tabula what we do is start with the negation of this, then it is not implies, that is not applicable now, it is not there is. Okay. So, we take not there is y p y implies say p a is new constant. Any t can be taken, let us write a. Now, not implies is applicable, so that gives there is y p y and not p a. Next, can you introduce p a, because a is already occurring, so you can't introduce. From there is y p y you have to give p b, right. Okay, let us go for p b. where does it close? It is not closing, fine, but this is one universal formula, so it can be reused. So let us go for B. So that gives not there is y Py implies Pb, B new. Is it new? Yes, it will be new provided we do not have this, but do we require new? We do not require new, right? It is universal formula, not there is, it is a universal rule. So we do not need new, though existential occurs, it is occurring after negation, right? So the rule says anything is allowed, so that is all right, fine. Then not there is not implies, that gives there is y Py and not Pb. Now the tabula closes. Okay. So even though you applied the heuristic that you use, there is first for all type of thing, next existential rules first, universal rules next, still there is repetition. Just go back to the tabular rules. In the tabular rules you have for each operator there is one. So that rule says, for all rule says, for each x x, then introduce x x by t for any term t, right. But for there is x x you have the restriction, you can introduce x x by t provided t is new, right. Similarly for the negations of those things, fine. So negation of for all you can introduce t to be new, negation of there is no need of new. See, we have the rules which says for all x x, then you get x x by t for any term t, but if it is there is x x, then you have to tell x x by t where t is new, let us say new constant, right. So if you introduce a should be a new constant to the path. Similarly when you go to negation of those things, you get not for all, there you need new, not there is no need of new, right. So that is why we had classification of those four things, two of them are existential, two of them are universal. So existential is there is x x, not for all x x, universal is the other two. So universal you can instantiate with any term, existential it should be a new constant, is that okay? But you see here we had to repeat anyway, not Pi here and again not Pb, the same universal rule has to be applied twice, universal formula we have to use twice, right. It is because of this constraint that this t should be a new constant, okay. But then from the reuse what do you observe? Even if it is not new, is it not enough to say that it has not been introduced by one existential quantifier or existential rule? See, if you take the other case, for example when you take this for each x, x implies y, suppose you use this rule first and keep there is x for the next use, we had put the heuristic because it was being repeated, right. Then what happens there? First for each x you have used, you have introduced some constant c, next the same constant you cannot use for the there exists, but if you use there exists first, then the other one you can use, there is no problem, right. So in essence the repetition of for all rules can be avoided by choosing the existential first, that is what we had done. Here now what happens, this constant a has been introduced by one universal rule, right. So it has the potentiality to be any constant. Why this a? It could have been any constant, by chance we have just taken a, we could have taken b also, right. Now when after this you are going for some particular thing, so with that particular thing again you introduce, so it could have been introduced there also. So which amounts to telling that a new constant need not be completely new, you can restrict a bit, you can say that it is new means it has not been introduced by any existential rule, that is enough, right. So, such repetitions can be avoided. So, now you see a generalization of the newness. So, you say that this constant is new, constant is new. So, new means new to the path if it has not been introduced to the path by an existential rule. But this is not sufficient, because in the premises also it could be free in the beginning, right. So, we have that anyway. So, along with this we should have also the constraint that it is not occurring in any of the premises used in that path, premises only, anywhere else it can be used, right. It can be introduced by one for all rule, no problem. It is not occurring in any premise used in the path, it is not introduced by any existential rule previous to it in the same path, that will give the newness, right. So, there are really two conditions on this newness. Once you become acquainted with it, you can make the tabula shorter, that is what it says. But if it is too complicated, you can forget it, you will again reinstantiate and then complete it, there is no harm, fine. Now, with these new things, what you can do is, from this point onwards you can change it. So, you can say just P A and it closes. So, you say A new, still you have to write A new, right, but now new means redefinition of new, that condition is to be seen. So, now this P A, why is it so? Because A is not in the premises, there is no premise here, it is in the negation of conclusion, there is no premise here, fine. So, A does not occur in the premises, A has not been introduced by any existential rule, there is no existential rule at all used till now, that is all. Okay. Let us see one more example. Let us see how the tabula proceeds with this. So, in the tabula we will start with this and the negation of this, right. So, let me start there itself, these two are given. Now, you have to develop the tabula. Okay. So, our heuristic says we should use this first, not this is universal now, not there is. So, anything can be instantiated, here some particular things we have to take. So, let us start with that. This one in 2 steps, right, 1, 2, 3 steps. So, you will come to not Q A, not Q B, not Q C and Q f of A comma B C. Okay. It will come to this A B C new, all are there exists. So, let us say x, when I take x I can introduce new constant A, fine. So, that gives there is y, there is z, not q A, not q y, not q z, q f of A y z, right. Next again there is y, I have to introduce another constant B, so introduced. Next there is z, so use another constant C, it will come like this. So, though it comes, it is not correct to write in one step, you have to write really 3 steps here, right. So, finally, it will come to this. Is that clear? Next we can use this. Fine, we want them to close negation. So, it looks we have to go for the similar substitutions, right. Let us see this, say x is a. So, when x is a, this gives not there is, this is universal. So, I can use any constant, same constants I can reuse. So, not there is y, not q a, I am taking steps here, not doing at a time. Okay. This comes from this, not there is. This one from the beginning, this entails this one. So, I have to start the tabula with premise and negation of the conclusion. I saved space. Okay. You will have to write it again once more. Take this one and then negation of this. Fine. Now, from this we get not there is y with instantiation x by a. Substitution is x by a, right. Then I go for b. So, that gives not of not q a and not q b and q of f of a b. Okay. Now, this one is not and rule. Okay. So, not and means it will be branching, but here it is stacking. So, I should use this first instead of going for this. Okay. Now, this one if I use, I get not q a, not in one step, again 3 steps, associativity will take care, right, but anyway they will stack. So, not q a, not q b, not q c and q f of a b c, okay, from this and. We wanted them to close, right. So, now we have to use this even if it branches. So, what are the branchings? In fact, it will be 2 branches now. One is not q a, another is not of not q b and q f of a b. Okay. Not of p and q, whole thing is q now. So, not of p and q is not p, another branch is not q. So, not of the whole thing. Okay. So, this q a, I have not q a, so that closes. I do not have to write q a now. I have not q a in the path, not q a, so they close. Now, similarly here we branch out again. So, that gives not q b and not q f of a b. This also closes because we have not q b on the path, but there it stops, it is not closing. So, we have to use this rule. This is universal, this can be reused. With what we should reuse? See, we have not of q f of a b, right, it will close with not will come from this not and this not. So, that is why he suggests you take x as f of a b, y as c. Reason? We have this, we also have this, any one of them might close if you take that way, right, because f of a b is already x, f of x y. So, this is f of a b, f of a b. So, this y must be closing with c, you have to choose y as c. Z, there is no z here, right, that is gone already. So, now we again reuse in this branch only, right. So, that gives not of not q f of a b, x as a b and not q C and Q f of x is f of a b, y as C, right. So, you can write here x is replaced by f of a b, y is replaced by C. This is the substitution used on the only universal here on this. Okay. So, once you use this is again branching rule. So, that gives rise to two branches, not q f of a b and again not q c and q f of a b c. So, this branch closes because you have not q f of a b. Now, this gives rise to two branches again, not q c, not q f of a b c, and we have not q c. So, that closes, this also closes, right. So, see the meaning of reuse. In fact, by the rules we should write it, we are not rewriting it, we know it is universal. So, we will try to reuse it. Okay, let us take one more example. Okay, you can try De Morgan's example, right. All horses are animals, therefore, all legs of horses are legs of animals. So, what is the symbolization? For each x, h x implies a x. Therefore, now you are writing straight away for the tabula. Okay, you have to prove this by tabula. So, next one is therefore, all legs of horses for each x, if x is a leg of some horse. So, L x and x is a leg of some horse, right. There is y, h y and L x y. Okay. There is a horse of which x is the leg, right. Then there is one animal of which x is the leg. So, in the tabula proof we start with the premise, and the negation of the conclusion. Okay. Then which one you should use first? This one. This is the existential rule, not for all. So, x will be instantiated a particular instance, so that this can never be used again. Okay. So, that gives not there is y, h y and say L b y implies there is y, a y and L b y. Fine. Next, not implies. So, that gives there is y, h y and L b y, and not of there is y, a y and L b y. fine. So, again this is existential. So, let us use first. So, that gives H B, B is already used, C and L B C. Well, you could have written that B is new here, and here similarly C new. We can't use the same B, and moreover B is already has been introduced to the path by one existential rule. So, it can never be used even in the relaxed condition. This gives HC, LBC. Okay. Now, there are two rules which we have not used yet. This universal, and then which one? This is also universal. These two we have not used. So, let us use the first one, see what happens. So, first one says H, what should I take? C is coming. So, let us take HC implies AC. So, for the universal rules, it becomes an almost unwritten rule that whatever constants have been used, use that. For the existential it is do not use that, for the universal use that, then it might close quickly. Okay. So, this gives rise to two branches, not HC and AC, and not HC closes. Now, you take up the other branch which was having SC. Okay. In this we have not used this universal rule. So, that gives not of, we will take C again, SC and LBC. So, that gives rise to two branches, not SC, not LBC, not AC closes, LBC also, that also closes. Is this set inconsistent? Let me take a total relation. Which is irreflexive and which is transitive. So, suppose I want to show this. So, once you ask like this, it means it is equivalent to asking for each x there is y p x y, for each x, for each y, for each z p x y and p y z implies p x z. Does this entail there is x p x x? Right. Fine. I am not saying that we are using RA, but tabular method itself. Tabular method says when you go for proving this, you take this and negation of the conclusion, so that it is inconsistent. So, RA is in the definition of the tabula, right. So, both the things are same, both the questions. So, now let us proceed. So, that means even if you started with this, you take not there is x x and then continue. So, we have now three sentences in the root. For each x there is y p x y, not there is x p x x, and for each x, for each y, for each z p x y and p y z implies p x z. Okay. All of them are universal rules. So, you have to start applying somewhere, right. So, let us say we will apply here or here, first one will do. Okay. That may give rise to there is. Okay. So, that gives there is y p, you want pay, okay. This is what it says, right. Next you will be getting P A B B new. This we have used once, it can be reused of course, it is universal. This one, this you want to use to not PA, fine. This is your PAB, there we have started, not PAA, okay. Here X as we are using this one, X as A, B, Z as A, okay. So, this gives rise to P A B and P B A implies P A A, it will give rise to two branches not of P A B and P B A, and P A A this closes, this gives rise to two branches not P A B. Let us take X as B. So, you get there is Y P B Y, it gives P B A, right, is it okay? But it is wrong. Why is it wrong? Problem is this, is it really inconsistent semantically? Can you give an example? It is easy here. Some infinite domain where it is satisfiable. Well, you take the set of natural numbers, interpret P as every natural number there is another natural number bigger than it, okay. Then this says transitivity less than relation is transitive, this says A is never less than A, all are satisfiable, okay. So, what tabula shows here is that you take in any finite domain it will be unsatisfiable, but it does not prove that it is satisfiable or unsatisfiable. Is it clear? So, this is the problem with our relaxation criterion. If you relax that way, then it might give problem. So, even if there is repetition, continue with the repetition, forget the relaxing idea, okay. Is it clear? Continue with the repetition. Now, the relaxation what you have done is not really correct, it is because of that it is showing to be inconsistent. Then you cannot prove completeness of the tabula or soundness of the tabula rather, it will not be sound even, because all that it will show in a finite domain it is unsatisfiable, but that is not the question. Question is whether the set is satisfiable or not in finite domain only. So, to that it will not be sound, right. So, then bear with the repetition and continue, that is the lesson, okay. Suppose you bear with the repetitions, then what will happen? You cannot introduce this PBA here, that is what it amounts to, everywhere else it was correct, there is no problem. Now, then what will you do? What will you do here? You have to give another C, right. So, you say P B C, that is what you will do. Okay. Then it looks you will be starting from this, just like PAB, it will be starting from PBC again, okay. It will introduce another D and then continues. So, tabula never terminates, it never closes and never stops, it remains open, right. But tabula does not say anything, it is silent, because once it closes it will tell you it is inconsistent, we stop there. If it does not close, continues infinitely, it does not say anything, we have to infer from it, okay. tabular does not say anything, tabular method. So, that means it signals that probably there is no finite model of it. Any finite set we have started with, we see it is not satisfiable. So, probably there is no finite model, that is what it says. So, instead of this, suppose you go for the systematic tabula, it will be clearer there, right, because we do not have any non deterministic choice. It will systematically find the all the domains necessary for it, all the elements in the domain. So, now it shows that probably there is a countable model, right, that is what we have done. We could give one countable model for the set, fine. But there is a relaxed criterion for the new constant, okay. Though the new constant idea we have introduced is not correct, there is a relaxed criterion for the new constant. See, that way you have to say not even introduced, nowhere it has occurred, you have told nowhere it has occurred. Now you relaxed it to too much, we say that it has not been introduced by any existential rule, okay. In fact, what you can do, it never occurs in any existential formula, that is what you need. Here it occurs in an existential formula, that is why you are not able to use it, right. With that you can continue. So, all that we have done today is simply found out how the tabula method is used for proving some theorems, and then we saw the trace of undecidability in the tabula method itself, whose answer will be there in somewhere else, as we have discussed in our last lecture.